ladies and gentlemen, and welcome to this IEEE webinar on the Fabless Foundry, the twin engines of the electronics industry. My name is Paolo Gargini, and I'm the chairman of the International Roadmap, and I will be one of the moderators. The other moderator is my colleague, Chetan.
Yes. Hello, everyone. I'm Chetan Patil. I'm a senior staff product engineer at Indie Semiconductor. And today I'm looking forward to hosting panelists Mustafa, Bo, Doug, and Michael. And I will hand it over to Paolo for starting this panel session with initial presentation.
Thank you, Chetan. I put some slides together of introduction. I'm essentially operating like an analyst, so I don't belong to any specific company, and so I can express opinions that my panelists would not be able to express. With this, this year is a very special year. We celebrate 100 years for the invention of the field effect transistor. As you can see, in 1925, Julius Lilienfeld filed the first of 7 patents that describe very in details how an FET works. In fact, the sketch below his picture shows how applying voltage to a contactless gate would build a channel that connects 2 regions adjacent to this gate. A team at Bell Labs in 1945 tried to demonstrate this transistor, and they thought it was only be a 6 months program. But the problem is that they were physicists and not chemists, and so they couldn't fully understand surface technology. And as you can see on the left-hand side, at some point frustrated, not only they approached the surface, but they went practically right through, injecting charges directly into the semiconductor. And first, Bardeen and Bratin put together the prototype to the left, and then Shockley worked for the next 4 or 5 weeks to obtain another prototype. And but eventually they demonstrated a transistor, even though it was not the field effect transistor. But since it was the first demonstration of this, they received 10 years later the Nobel Prize for demonstrating a transistor. They tried to file patents, but all the patents were infringing on Lilienfeld, so the Nobel Prize was exclusively for the demonstration. But slowly the transistor, made it into the consumer electronics. And you can see that it essentially was a little messy, but it could work. This my radio. And you can see that it was rather simple to put together. You go to a place equivalent to Radio Shack and you buy the components. It didn't cost too much. And on the left-hand side, I'm showing how you would solder the different components to the board. And you only needed a hot tip and a wire. The only thing that I want to point out that the wire was made on tin lead. That is the key component. The derivative of this is the key component on the flip chip. So as you can see, the technology in this form existed already a long time ago. But eventually, the field effect transistor was indeed developed. And in 1970, the first memory, 256-bit. I know that you used to megabit, gigabit, hexa, and so forth. This was 256-bit, period. But it was working. However, in the next 5 years, multiple companies in Santa Clara Valley began building this kind of transistor, this kind of devices, and that's where the name Silicon Valley was derived. This was a new, different kind of company. Essentially, these companies, the integrated device manufacturer, had all the capability from the circuit design, fabrication, test, packaging, marketing, and sales. This was extremely valuable. However, you see the red wall that I put around it. There was no alternative. You either were inside one of these companies or you were on the outside. And so this was a positive, but it had negative elements that you'll see in the next few slides. The point is that this company wanted to run high volume manufacturing, so they only ran what it was convenient for them. The ultimate example is what happened with the PC market. With the PC market, essentially IBM wanted to build the PC, hire two suppliers, Intel and Microsoft. They were simply supposed to be the suppliers to IBM. But you can see on the left-hand side that the suppliers to completely charge and control the market, whereas all the producer of PCs were fighting. You see, IBM couldn't even reach the 10% market share in this. So this was a very uh, kind of upside down market. In addition, what happened, these companies were concentrated in making the highest possible revenue. And that's where the relation with the foundry began. At that time, whenever something was approaching the $25, it was more convenient to send it to a foundry that really do it internally because it freed up space and equipment. In 1990 or so, I remember we had like 13 foundries working on the overflow for Intel. This, had this relation was perfect. Essentially the IDM would make the big money and the foundry will collect device that cost less, but they still were making money. And however, this model shows the limitations in 2006. At that time, Steve Jobs walked into Intel, went directly to the CEO, and offered Intel to be a foundry for a new revolutionary phone that he had devised. And he said that he wanted Intel to work like a pure foundry, and he was offering something in the $10 to $20 to build the chip. You can see the line that I kept at the bottom that was way below what Intel was willing to receive for any of these. And so essentially it was kindly shown to the door and nothing would have happened with this if the only method of making chips was through the IDMs. Fortunately, the foundry system existed. And so in 2007, you can mark this historical date on June 29, the device was presented. And was this a success? This photograph on Fifth Avenue of people waiting to go and get the device. One thing, I had a group that would do reverse engineering. I have to say that the technology was not that great. The layout was not that great, but the product was great. And this one really marks an important element that had been forgotten with the PC era, that essentially what sells is the product, not the technology. And so even though the technology was shaky, the design was shaky, but the product was great and it was selling in very high volume. And so I want to show you something to say was Steve Jobs proposing something that was not reasonable. I took the build of material from two iPhones, the iPhone 4 and the iPhone 16. And you can see with the red arrows, this is the cost of the SoC. Now, this cost includes four elements, the cost of the chip, testing, packaging, and the IPs. And you can see that what Steve was asking was pretty reasonable. Actually, if you look at the top, the most expensive item is not the SoC, but it's really the display. And now with these complex cameras, these are adding additional cost that is completely unrelated to the SoC. In fact, I extracted out of all the bill of materials the cost of the loaded cost of the SoC, that is the green line, and you can see has been very well behaved. One of the explanation is if you look up above is the die size. of the Apple products. With the exception of three excursions, it stays very close to 100 millimeter square. And on a 300 millimeter wafer, to get 624 dies. So just, these numbers to the right have no reference to real numbers, just to give you a flavor that suppose the total cost loaded with all the testing, everything of a wafer was $10,000, and you have 400 good dies, like in the initial phases, the cost would be $25. So this was perfectly adequate. So, however, something occurred that we all went through, in 2020, 2021 with the pandemic, and everybody realized that globalization was no longer a dream of some economists in the 80s, but it had actually occurred, and the supply chain was widespread. But one item attracted the attention of everybody that was essentially semiconductor that had become so important for the economy. And this chart shown by SIA was presenting that in 1990, in the 90s, was 37% of the IC were built in the United States, and only 12% was built, going for 10%. Now, I was on the SIA board from 2000 to 2010, and I pointed this element, but at that point, everybody said, well, Intel, TSMC, and Samsung are going to take care of it. We don't need to do anything. Now, the next slide has some numbers, but don't get lost in the number. I only want to point out the item circled in red and blue. I presented from 2020 to 2023, almost every 2 months, to different organizations, NIST, NSF, DoD, and so forth, try to rationalize what they were seeing. And you can see here, I pasted together from IC Insight the ranking of the top 10 company from 1993, 2000, 2008, and then pre and post pandemic. And you can see that indeed in the 90s, 37% of the semiconductor were built, IC were built in the United States. And if you look at the market share of the three IDMs that appear in the list, was 37% among the top 10. And then as you go from left to right, you can see that in 2008, following the example of Apple, Qualcomm ranked for the first time a fabless company in the top 10. And by the time you get to 2021, there were altogether four companies. So altogether, the market share have grown from 37% to over 60. And so I put, in a single slide, on one hand in red, the percentage of semiconductor made in the United States, but on the other hand, the market share of the United States. And so, the point was, it's not that we had to invent a new system. The system works perfectly. We just need to make it more appropriate. And so at that time, there was discussion of what to do. You can see in the lower left, this is 2021. And Intel was building at that time Fab 52 and 62, so it was already well established in Arizona. And the TSMC had announced to make a couple of fabs, but I look at the land, I said they can easily put four factories there. And so, the NSTC, it was perfect on Arizona State. They had inherited the Motorola clean room. So this is the background, and now let's see to the future, okay? So the first phase is economics. So you have to act according to economics. In the long run, economics demand what the market will do. And so I took this from TSMC Q1 report of this year. You can see this is reported in the publication. And then my contribution, I put together the pie chart right below that show who the major customers, regions, of TSMC are. And so TSMC responded appropriately, essentially building factories in these regions. And so providing more security to the different regions that the supply chain was now within their region. And I had estimated 4 factories for TSMC, but going to this U-shaped arrangement, you can see that they can actually build 6 factories that will be functional by the end of this decade. The next element is technology. During the pandemic, you missed a lot of action because, of course, you are busy with something else. And so in 2022, all of a sudden, the world was shocked. There was something that never heard about. There was, AI. And you can see that in 2 months, it reached the 100 million users. But this was not something that had happened, overnight. In 2018, you can see Bill Dolly that presented at the VLSI symposium his results that show that essentially, after 10 years of work, he had managed to configure a GPU in the appropriate configuration so that it would solve the AI problems. And actually, I woke up, I was attending this conference. I asked Bill if I could use one of his slides, that is the one to the right, that I published in the IRDS 2018 executive summary, say the AI problem has been solved architecturally. And all of this happened with Hopper, and you can see the die size of Hopper is 114 millimeter square. That is up against the limit of what a scanner can do. So how come then, if this was a limit, the AI has proceeded so quickly, so well? Well, because it's using a technology that was developed 30 years ago. Essentially, the first person to say that no exponential lasts forever was Gordon Moore. And so around 1989, 1994, he has several questions, one of which was, what are we going to do once we reach the limits of scaling and die size? And so diligently we went to work and produced this prototype. It was not for sale, it was just to prove the point for Gordon. And as you can see, it has all the elements. Essentially, it has the processor, voltage regulator, static RAM, drum. But most of all, this was built on a silicon substrate with multi-layer of interconnection. So this technology was available 30 years ago. So it's no surprise that then both Blackwell and Rubin were able to use 2 dies and 4 dies respectively. And now you heard all different kind of names, but in the end, they all concentrated on a single concept. They all have a little sliver of silicon, cost saving. Packaging guy are very conscious about costs, and then progressively this is becoming more extended. So they're just variation on the theme, but the technology is ready available. So that's why innovation in AI is progressing so quickly, because technology is not a concern. And so if you look at the future, now we are expecting to hear something eventually about Feynman, but if I make a back of the envelope calculation, maybe 2, 4 will be 8 GPUs. We'll see. So in conclusion, there are 2 themes for this discussion. One is how is this fabless foundry model adjusting to the new reality? And secondly, how can we extend this to other application? And so with this, I would like to conclude this part, and then let's go to presentation from the panelists. Chetan?
Yes, so thank you, Paulo. It was a very interesting brief overview of the history of our last almost 40 years. Now, I would like to invite Mustafa, Director of Engineering at Qualcomm, to come to present slide decks and also a brief introduction.
Thank you, Paulo. Thank you, Chetan. So I will give a short teaser statement about what as Fabless we are thinking for basically making the Fabless design and foundry manufacturing, basically shaking hands together to realize the system. So I'm Mustafa Badaroğlu, working as Director of Engineering for AI, chiplet and system technology and system architect basically also managing the vendors as well as IMEC interaction as basically for enablement of the supply chain. So if we look at basically what is driving the silicon volume is all about parallelization. So AI is a parallel system. Also is a very good system for also high volume. So basically, you have a lot of chips distributed across the cloud, edge cloud, and on-device AI. And also these are not independent systems. Basically, they are interconnected either with wire or wirelessly all together for the single workload. So that's also very, very interesting. So this is actually a world of perfect parallelism and also a driver for economics of semiconductor. So the essence of it is actually how to make it distributed, basically bringing elements of distributed AI computing using, for instance, multimodal AI, and also IoT, merging all IoT elements, but also bringing high performance computing to edge devices like our AI PC, mobile phone, as well as a server in the car for handling both infotainment as well as safe driving. So that's very, very good view. And we are at the start of this and basically building now constituting elements to connect cloud to the edge to make this happen. So basically this system vision is so important. Having the awareness of system vision across the different stakeholders, making this happen. It's not a single company effort. It's a collaborative work. But the most important thing, what is driving it, everyone knows what to do. So what is missing in the system, grand challenges, and to make it happen, not like a single chip, but a system basically that is integrating the work of different companies, different grand challenges solved together in this circle. So you have one side, material and equipment vendors realizing the capital investment in the R&D organizations like IMEC, LETI, as well as different hubs for proof of the concept module development, as well as the device readiness and material testing. And then this is actually shown to foundries and the OSATs as a working solution, really years advance, and then making the CapEx investment to bringing things to high volume manufacturing. And then the fabless and system companies basically driving the specs as well as basically a commitment to a system product without basically a contractual agreement, showing that this is the system that is needed, and then we need to build together. And basically, that way, the industry is able to do massive amounts of billions of dollars of investment for making this happen. One good example is EUV high-NA transition from EUV. The tool itself is several hundreds of million dollars each tool, and you had to do a significant investment of it in the fab. So this is all because of the fact that old way of designing things, like you get a PDK, you do an independent design, you tape out, Foundry process it, you send to OSAT testing. It's not anymore unidirectional, but you have awareness of what the technology needs. Sometimes you identify gaps. You do path finding before getting the PDK and make this cycle work. And then one interesting thing, the innovation element. So this circle also looks like more like companies are talking to each other but less awareness of to what's the academy build up and the innovations coming from on fundamental research as well as new young engineers making actually contributions to the flow and coming in. So, for instance, in roadmap activities, which are open domain, which is distributed by IRDS, IEEE, as an example, actually driving and centralized communication, what the consensus of the industry is, and then making basically communicating the system vision as well as what are the missing elements of the technology and what is expected in the roadmap. And then this is basically driving also the 5 to 10 years fundamental research, extended things beyond the decade. So basically, today's flow is we really start from the package. So and the package of packages. So basically, the chiplets. Form factor very important. What the limits of the physics, thermal, material compatibility, all these aspects. So rather than chip deriving the package now, the end system derives what needs to be designed in the system, as well as the missing system fabrics complemented by the package, what we call a system technology co-optimization. And basically, you see really a co-development of two technologies each other, but this cannot be done with only one technology wave here. So in one side, you have the two basically continuous scaling of the energy efficient, area efficient computing, which is basically transitioning from FinFET to gate-all-around device and a multi-tier gate-all-around device with a lot of system fabric enabling a truly 3D VLSI system. And then you have to also interconnect them, making this 2.5D and 3D ready to make large systems for scale up and scale out systems for memory and logic, 3D memory and logic, a lot of backside functions, making the chiplet compatible for rest of the system, and also the the highly basically advanced interposers, creating a interconnect of the chiplets with different needs of the system, like power, clocking, networking, as well as even some distributed memory, like CSL architectures topologies now developing for convergence of memory pools and the memory together with the complete chiplets that are put all in the same reticle. So I just want to end with some takeaway statements. So grand challenges of distributed AI computing is making this happen. We need a lot of silicon. So economics is there. Also system fabrics are quite well known. Now there's consensus. It's not anymore PPA, but it's a really TCO, power, and the thermal all together is now driving the scalability of these systems. And to make this happen, we need a collaborative work to realize the system vision. So basically, looking at classical VLSI technology, proof of concept readiness, such that the high investments are working out, and to derive this continuous leading edge equipment investment, access to advanced patterning and device vehicles through consortia, and ecosystem, such ecosystem creating as basically understanding of a consensus across the system that all companies invest and make it happen together. And all besides the chip, also basically filling the holes with the system fabrics enabling chiplets, power, I/O for full system scale-up and scale-out solutions. And then this all requires a multi-dimensional down selection through SDCO, a new device architecture for intra and inter-chiplet communication for advanced system interconnect with advanced packaging, and also brings in the memory and the I/O readiness to connect the compute capability to each other and provide the data that compute needs with high bandwidth memory in applications in mobile compute cloud applications. So that's the message I want to lay out. So before Q&A, yeah, thank you so much.
Thank you, Mustafa. This was like the two main points you mentioned is the collaboration and also the system-driven development that is happening as the industry is moving forward. And thanks for sharing the insights. So we will take the Q&A at the end of the closing session. I will now like to invite Michael Wang from TSMC. He's a Senior Director of Strategic Analysis and Forecast. Michael, if you could like to go ahead.
Okay. Before I start, I'm Michael Wang working for TSMC. My main responsibility is to do the market forecast and also the demand to TSMC. As well, I have to provide the strategic recommendation to the executive. That's about my main role to the company. All right. So to start with, in the past 25 years, we experienced the continued growth of the whole semiconductor industry, especially in the first 20 years back to year 2000 to year 2020. The semiconductor excluding memory market to grow at about 4% CAGR, although we experienced two major cycles after dot-com bubble and financial crisis. And then after the evolving of COVID-19, actually, the whole semiconductor excluding memory market to grow at a accelerating momentum of 10% CAGR. So in combined of total, the whole excluding memory market grows at 11% in the past 25 years. Now, if you look at the breakdown of the customer type, the players type, you can see to start with, IDM excluding memory share majority of the market. And then along with the support from foundries, Fabless continue to gain share from the overall market and then already reach more than 55% of the share to total semiconductor excluding memory for this year. And then you can see also system company continue to doing their captive ASIC or COT. They also share certain position of the whole market. So as a whole, you can see the semiconductor excluding memory market, over 80% of the growth in the past 25 years contributed by Fabless as well as system companies. So Fabless really drive the overall semiconductor excluding memory market growth in the past 25 years. So along with the semiconductor excluding memory market growth, you can see the conventional foundry, I called it Foundry 1.0, also grows accordingly. In the first 20 years, or starting from year 2000 to year 2020, the compound annual growth rate reached 9% in the past 20 years. And in the latest 5 years, the CAGR accelerated to 16% growth. And now the foundry market already reached close to 165 billion, likely for this year. So along with the foundry and IDM become intertwined in the past years, also packaging and testing already became integrated part of the foundry service. So here I would like to introduce the concept of Foundry 2.0. Actually, this concept is first initiated by our Chairman and CEO in last year. The concept is basically combined with conventional Foundry 1.0, the term I just shared in last page, also IDM internal services, starting from wafer, testing, packaging, and mask making, and conventional OSAT companies. All those combined as the term for Foundry 2.0. So conventional Foundry 1.0 share about more than 55% contribution under the Foundry 2.0 competition. But still, all in all, the Foundry 2.0 vision takes a holistic approach to industry evolution, recognizing the system level integration is the future, just like Mustafa just mentioned in his presentation. So along with the new defined Foundry 2.0 market, in the past 10 years, the Foundry 2.0 market TAM grows at about 7%. And we believe in the coming next 5 years, the CAGR will further accelerate it to 10% growth. And this growth also will close to the overall semiconductor excluding memory market, along with the Foundry 2.0 actually is the cost of goods sold of the whole semiconductor excluding memory market. And this also support the whole semiconductor market to grow, exceed $1 trillion by the end of this decade. And this summarize my report.
Thank you, Michael. That was very insightful. I wanted to show that this model is extended outside the silicon production. So thank you.
I'm glad to be here today. I'm Doug Sparks. I'm the CEO of M2M Technologies, which is a consulting firm that focuses on semiconductor MEMS and sensors. I've worked in startups, IDMs, and foundries across the world, from the US, China, Japan, and Europe, in a variety of fields. I'm going to mainly talk a little bit, just quickly, about what MEMS are. It's really, Bo kind of talked about it a little bit, but it's making silicon wafers with moving parts or three-dimensional parts, and these are often etched into surfaces through the whole wafer and then stacked up through wafer bonding. So these are commonly found in automobiles, smartphones, smartwatches, and now they're starting to transfer into data centers as we move from copper to photonics to optical, data transmission. So you're bonding MEMS wafers to CMOS. And obviously, MEMS devices are different than what TSMC would typically run, or a typical IC foundry, because of the three-dimensional nature. And there's many times there's very strange materials that preclude them from being in a traditional foundry. And one company that I'm helping out with business development is InchFab, and it focuses on startups. Because
the slides are not moving, so if you can switch.
Okay, sorry.
Before, okay.
Okay, is that good? So this is just showing what MEMS are: micro electrical and mechanical systems, moving parts, gyros, pressure sensors, waveguides, for example, and mirror arrays. And then one of the companies that I'm working with is InchFab, and they're kind of focusing on startups, because not a lot of startups, when they come up with an idea, a new optical product, for example, or a new chemical sensor, they're in a university, and they don't have millions of dollars to go right to a big foundry. So they need a smaller foundry. And for InchFab, they use smaller diameter wafers, lower capex, and so they have about a 10x lower project cost, foundry cost, than you might get at a 200 or 300 millimeter foundry. So it's kind of ideal for the post-university stage of a fabless startup. And then something, in addition to foundry services, InchFab also offers, they just started offering this year, mini fabs. So a university or a government institute or a startup that's in a niche industry, for under $15 million can have their own wafer fab. So you can put this in an office complex. And we're really seeing a lot of traction in developing countries that don't have semiconductor infrastructure. But they from a sovereign standpoint, they want to have their own clean room. So from question standpoint, I just want to talk to fabless people. They don't have a big budget, but they still need a foundry, and that's something that needs to be serviced. Thanks.
Thank you, Douglas. Thank you very much. So one thing that we did, explaining to the audience what you just saw, we had an opportunity to share the questions that Chetan and I had in mind and collected. And so that the presentation, we're already by and large addressing these questions in particular. But we still have time for asking a quick question still. So Mustafa, simply a few sentences because you explained most of this already. How is the Fabless Foundry model adapting to chiplet-based SoC design where system-level thinking is really dominant? How is this changing the equation?
Yeah, thank you, Paolo. It's a great question. So for the chiplet-based design, the most important thing, you have to really start from the board level. Sometimes an expensive chip can end up with a low total cost ownership in the overall system. So aspect ratio definition and everything, basically, without even the PDK, basically having a common understanding of what foundational elements are and the supply chain readiness, to bring the heterogeneous system working tandem to each other. So basically, we make it sure that the companies that takes inputs from the foundry or that needs to provide inputs to foundry, we connect them together to make this full system enabled. So it's an example of the collaborative work. Even we work on the protocols between these companies such that one chiplet can be ported from one company to another, and then the assembly house also interacting in the early phase of the product development. So basically, there is no change, but more collaborative, basically bringing thermal solution, board solution, assembly solution, foundry all together in the beginning of the project, and then making sure that that works. Then we start the design. So on the design, you have to make it sure that the chiplets are talking to each other. Chiplet can be integratable. And to be able to do that, we work with multiple PDKs and assembly design kit to make it happen. Then we work hard to reduce the cycle time because the chiplets, although it's a lot of reuse, but the cycle time is much longer. So that's why we take advantage of design reuse and also reuse of the chiplets to reduce the cycle time, to bring a 2.5D and 3D system short in time to final product. So no change, Paolo, short answer, but a lot of collaboration of multiple companies at the start of the project and then creating basically a pipe cleaner run across the companies before we start the product. So that's
Thank you,
how we
Mustafa.
handle.
Chetan?
Yeah, so I would like to take one live queue question which came in, and Doug, maybe you can, this is for you. So the question is, what is the biggest challenges that will be there to continue to bring the semiconductor manufacturing to the US?
Well, the biggest challenge is to bring it back to the US.
Yes.
You're saying?
Yeah.
Yeah. Well, I mean, it's all profit margin, costs. I mean, we can build the infrastructure. Can we make it as at the same profit margin that TSMC can do that in Taiwan? That's a big challenge. OSATs are widely distributed across Asia. I think that's going to be the biggest challenge for the U.S. is being able to provide OSAT services and assembly at the price points you can see throughout, China, South Korea, Philippines and places like that. So I think it's all economics will be the biggest challenge. And then there's, of course, workforce development. So I would say economics and workforce development be the big challenges to bringing the supply chain back to the U.S.
Okay, thank you, Doug. So there's Michael, for the question is for you. There's a lot of changes happening in the market in terms of AI, edge, automotive, alternate vehicles, and a lot of fabless companies are coming in. So how does TSMC ensures and helps these fabless company grow their model by providing the services? Michael, you're on mute.
Sorry, my bad. Okay, so I believe the diversity actually plays into the strengths of TSMC, and our mission is to be the trusted technology and capacity provider for the global IC industry. So, as the target to be everyone's foundry is our DNA to serve a highly diversified customer and product. And for your record, actually, we now already have close to 300 technologies today. And also, I believe, this is the most comprehensive technology portfolio in the market. And this technology portfolio can serve more than 500 customers and over 12,000 products in our production line today. So what else can we do to add to this already solid foundation and continue helping our customer to scale? Again, we continue to strengthen what we have been good at. I would like to address from three angles. The first, maintain our technology leadership and broaden our portfolio. Like our N2 will run into volume production by end of this year, and also we already announced our A14 and to be already in the line. And we continue to invest heavily in cutting-edge technology nodes, enrich our specialty technology offering, and we also put a lot of focus on heterogeneous integration through our advanced packaging technology such as CoWoS and SOIC. And second, we expand our capacity and global footprint to provide geographic flexibility to our customers. We continue strategically expand our manufacturing footprint, including building gigafab for leading-edge technologies, and also creating dedicated facility for specialties. And our global footprint in Taiwan, in US, China, Japan, and Europe already help customers improving supply chain resiliency. And the third, we continue to focus on customer-centric collaboration and cultivate ecosystem partnerships. As design and manufacturing become increasingly complex, design technology co-optimization, DTCO, or even STCO, system technology co-optimization, has become more critical. And by working with customer from the early design stage and close partnership with ecosystem, including EDA, IP vendor, we optimize our process technology to meet the stringent need of PPAC, power, performance, area, and also cost. So with all the three directions I just mentioned, we believe we can continue to bring diversity to the market long-term growth. That's my thought.
Thank you, Michael. Paulo, want to answer?
Bo, can you see my screen?
Yes, Paulo.
Okay. So if you look at the evolution that we have seen, in over 60 years, so we went from the integrated circuit demonstration in the 60s, and now this on the right-hand side is my rendition of what a data center looks like. Essentially, the racks represent the new transistors, and they're all interconnected. And this is the reality that we are going in. And in this reality, if you look at the results of 2024, something that had never happened before, you can see that NVIDIA, a fabless company, ranked third in 2024. And this had never happened before. Of course, this was the cooperation with TSMC producing the devices. So if you look at this moment for the US, in conjunction to what Michael already stated for the big picture, if you look at the yellow bar represents in the top 10 the revenue of the fabless as opposed to the IDM that has surpassed the level. So we began at the beginning, with my first slide that we are celebrating the 100 years of the invention of the FET. And as I said in the beginning, since I don't belong to any company, I can make my assessment as an analyst of what I see another accomplishment of 2025. My prediction is that in 2025, NVIDIA will end up for the first time ranking ahead of the IDMs, of course, with the help of TSMC. And so this will really mark another key point in the evolution of the semiconductor manufacturing, that the fabless foundry system will become the leading element in driving the growth of the electronic industry. So with this, I would like to thank all the panelists that have participated today. As I said, we provided them with the questions, so they were already embedded in some way in their presentation. Continue sending questions, and I'd like to thank all the participants for staying. Still have another couple of sentences, but Chetan, would you like to say a few words?
Yep. No, thank you to all the panelists. Thanks, Mustafa, Abu, Doug, and Michael. This was really interesting panel session and all the details shared. And definitely, hopefully, all the participants learned about the past, present, and also the future of where both the technology and the Foundry fabless model is heading.
Okay, and like in the Oscar, in concluding, I have to thank our sponsor, Kathy Hayashi and Kathy Grease, that allows this event to occur, and of course Ipsida Praja that really made sure that we presented everything correctly. So, as I say, this will go on demand tomorrow. And we will keep collecting questions and we'll send the questions to the panelists and we'll post the answer on the website. With this, I thank all the attendees that have remained online even beyond the time. Thank you. Without you, it would have been meaningless to have this event. And so with this, Ipsida, do you want to take this webinar to the end?
Sure. Thank you, Paolo.
Thank you, everyone.
Thank you.
Thank you.